In this section, we're going to be talking about a particular class of differential equations that are called separable differential equations. The word separable is just a sort of shortened way of saying separatable. So these are equations that can be separated in a particular way. Here's what I mean. This equation has been separated so that all the y's, including the dy, are on one side of the equation, and all the t's, including the dt, are on the other side of the equation. But it might not have started out that way. Oftentimes you see equations that look like this. dy dt equals 2t over y squared. This equation is still separable. It's just this equation rewritten into the form that it's probably been given originally. Notice that we have a ratio of differentials here, dy dt, and that's equal to some combination of functions, one in terms of t and one in terms of y. If I can rewrite this equation so that it can be separated, y's on one side, t's on the other, then we say that it's separable. In general, we say that a differential equation is separable if it can be written in the form f of y dy equals g of t dt. T and y may not be the variables involved. It may be something like h of x dx equals k of t dt, or p of x dx equals q of m dm. Really, I could use any variables, or an equation can be given using any variables, but each of these has the same form. And because of that, it's going to be easy to solve this differential equation simply by taking the integral of both sides. I can do that with any of these. Now that they're in this form, I can do that with any of these. I've erased those integral symbols again because really what I want to leave this screen with at the end is this definition of a separable differential equation. All right, let's take a look at an example. Solve the separable differential equation dy dx equals x squared over y squared. Now to start with, I want to make a note that you will not always be told that the differential equation you're about to try to solve is separable, or in any other form for that matter. We're just learning this technique, so I've put that in there. Your textbook does the same thing. It tells you in the exercises to solve the separable differential equation. But on a quiz, for example, at the end of a unit, you'll just be asked to solve some differential equations, and you'll need to be able to determine whether that differential equation is separable or some other form. The trick with these is pretty simple. Let's multiply both sides by dx and multiply both sides by y squared. Having done that, I can now cancel the y squared on this side, and I can cancel the dx on this side, and I have this equation y squared dy equals x squared dx. And all I need to do now is take the integral of both sides. I've made a copy of that so that as I integrate both sides, we can still see the equation here that we're integrating both sides of. So as you go back to look at this in your notes, you have this line and this line. That's not strictly speaking necessary on a quiz, for example, but it may help you process the steps that are necessary to solve a problem like this. Well, the rest should be pretty easy for you. This is just the integral of y squared. So I get y cubed over 3. And this is just the integral of x squared. So I get x cubed over 3. It's important to note that I can do that because I'm integrating with respect to y. So that gives me this. And here on the right-hand side, I'm integrating with respect to x. If you've taken Calculus 3, don't forget that this is single integral calculus, and you're not expected to do anything with the two different variables. This is not a double integral we're taking here. Now, there's something else that's important to note, and that is anytime you take an indefinite integral, you have a plus c. I'm going to call this one plus c1 and this one c2, since they may be different. The thing is, we can get away with really only writing one of these, because, for example, if I subtract c1 from both sides, I now have the equation y cubed over 3 equals x cubed over 3 plus one constant minus another. Well, you take one constant and add it to another or subtract another, you still just get a constant. So I'm just going to call it c. In fact, I could have done that up here. I could just have said plus c, and I'd have ended up with the same thing. So now I have y cubed over 3 equals x cubed over 3 plus c. But I'm trying to solve this differential equation, which means I'm looking for y. What is y in terms of x? So I need to continue with the algebra here. Let's go ahead and call this c, c3 for now. If I multiply both sides by 3, I get y cubed equals x cubed plus 3c3. Well, guess what? That's just a constant. c3 is a constant, and 3 times that constant is another constant. Taking the cube root of both sides, I get y equals, I can either write this as the cube root of, or as the quantity, the expression, to the power of 1/3. I think I'll do that. X cubed plus c4 is just a constant. Let's just call it c at this point, to the power of 1/3. Now, here I have a solution to this differential equation. I have an equation of y in terms of x. So this is a general solution, because I don't know what c is, a general solution for this differential equation. Let's take a minute and look at a sort of subcategory of differential equations. These are called initial value problems, because if in addition to the differential equation I give you at the beginning, I also give you some initial conditions. For example, y of 0 equals 2. Then you have more information, and you can use that information down here to find a particular solution. This is the general solution, and it will satisfy any conditions that might be met. When in this particular case, when x is 0, y is 2. But what if x was 1? What would y be then? What if x was -1? What is y in that case? Well, we're only given one set of conditions, so we can only use those. But with that, instead of a graph containing multiple examples from a family of curves, we're going to be able to draw just the one curve that comes from these conditions. All I need to do here is plug my 2 in for y and my 0 in for x, and the rest is like this. And algebraically now I can solve this. 0 cubed is 0, plus c, c to the 1/3, cube both sides, and I get c equals 8. So under these initial conditions, the value of c is 8. This is not the particular solution. A lot of students will write c equals 8 as their answer to the particular solution for these conditions. But it's not. It's just the value of c. The particular solution is the general solution rewritten, but with c, the now known value of c, in place. That's an important distinction. That is just the value of c, not the particular solution. I just noticed I've made a mistake here. This should be to the 1/3 power, not to the 1/2 power. And I'll make the observation here. I'm having trouble with my pen tool. There we go. I'll make the observation that this is the cube root of x cubed plus 8. That's what that to the power of 1/3 means, by way of reminder. This is not, however, equal to x plus 2. It's tempting, but I know you've seen this in algebra. These two expressions are not equivalent, right? If you cube this, you will not get x cubed plus 8. You'll get x cubed plus, let's think now, 6x squared plus 6x plus 4 plus 8, something like that. You will not get x cubed plus 8. So these are not equivalent. Be careful when you're simplifying this. It's very tempting, but don't do it. Okay, let's take a look at a couple more examples of differential equations. Here's one, dy dt instead of dx is negative t over y. Here's another one, dy dx equals 6x squared over 2y plus cosine of y. And here's a third one, dt dp equals p squared t. All right, hopefully you can see a pattern here. This is dy dt and this is t over y, t things over y things. Dy dx is x things over y things. Dt dp is t things but not over p things. But we'll be able to rewrite this. Remember that a differential equation, a separable differential equation, is one that can be written in the form one function f of x dx equals g of y dy, right, in that form. This one can be written in this form. These can also, they're not in that form yet, but they can be written in that form. And that's the step we need to take first. This one is simply going to be, so we'll multiply both sides by dt, and we'll multiply both sides by y, which lets me cancel the y's here and the dt's here, and I get y dy equals negative t dt, which when I integrate gives me y squared over 2 equals negative t squared over 2 plus some constant. Remember that I technically have a constant here and a constant here because I'm integrating here with respect to y and here with respect to t. But algebraically, I can just add this constant to both sides, so I can combine them. Multiplying by both sides by 2, I get y squared equals negative t squared plus 2c, but 2 times, I'll write it as 2c. 2c is just a constant, right? C is a constant, 2 times that is another constant. Take the square root of both sides. Y equals the square root of negative t squared plus c. There's my solution, my general solution to this differential equation. This one is, I'm going to take the same approach. I'm going to multiply both sides by 2y plus cosine of y times 2y plus cosine of y. And I'm going to multiply both sides by dx. So I can cancel the dx's here and the y expressions here. And now I have 2y plus cosine y dy equals 6x squared dx. And then integrate both sides. Here I'm integrating with respect to y, and all I have here are y's. Here I'm integrating with respect to x, and all I have here are x's. That's what allows me to do this, and that's what makes these separable. If I can separate the expressions so that all the y's are on one side and all the x's on the other, then I can do that separation, and then I can integrate easily. This will be 2 times y squared over 2 plus the integral of cosine is sine because the derivative of sine is cosine. That's a positive sine. Plus c, but I'm going to save it and put that on the other side. 6 times x cubed over 3, which will simplify, and there's my plus c. Canceling these and reducing this, I get y squared plus the sine of y equals 2x cubed plus c. Now in this case, that's as far as I can take it. I can't solve this for y explicitly, but that's okay because remember way back in Calculus 1, we learned how to differentiate implicitly. We can be given functions that look like this and we can still differentiate them. Clearly we can integrate them as well, right? So it's okay if it's in this form, but if you can solve it for y, you should. All right, let's take a look at this last one here. I can see that multiplying both sides by dp is going to let me cancel the dp on this side. But how do I get rid of this t? If I divide both sides by t, then I end up with something over t. Well, but that's exactly what I need to do. So if I divide this by t, and I divide this by t, I get the equation 1 over t dt equals p squared dp. Well, the integral of 1 over t is the natural log of t. And the integral of p squared dp is p cubed over 3 plus c. All right, now I should solve this for the dependent variable if I can, but how do I know which one is the dependent variable? Well, if we go back to the original differential equation, you can see that this is a differential, this is a derivative that has been taken of t in terms of p. That tells me that t is the dependent variable. So I need to solve this for t, not p. Solving for t means raising both sides, exponentiating both sides. So I tend to write this like this. It's kind of cheating, but e to the power of, e to the power of. I've chosen e because I have a natural log here. That's going to give me absolute value of t is equal to e to the power of, I'm going to write this as 1/3 p cubed plus c. I will run out of room probably more times than I won't on these videos. I've kind of got used to that with myself. But in this case, I think that means I'm going to go back over here to try to write the next step. T is always going to be positive because e is positive, e to the power of 1/3 is positive, e to the power of any other power, e to any power is positive. Right? Even if your power is negative, your graph is going to look like this. And the value is always going to be positive. The value of y there, or in this case t, is always going to be positive. So I don't need those absolute value bars anymore. It means I can write this as t equals. Now I'm going to do a little bit of algebra. I can take, because I have a sum, an exponent with a sum in it, I'm going to rewrite that as e to this power times e to this power. So I get e to the 1/3 p cubed times e to the c. Well, e to any power, e is a constant, c is a constant, this is a constant. So that is t equals e to the, sorry, let me back up. I'm going to move this in front. But this time I'm going to call it k, just to change its name a little bit. E to some constant is a constant, but it's not the same as c. I could call this one c1 and this one c2 if I wanted, but I'm just going to call it k. All right, e to the 1/3 p cubed. And this is my general solution for this differential equation. The trick here was to recognizing that I could separate the p's and the t's. I could get all the t's on this side, but what that meant was that I had a 1 over, and that's fine. And instead of multiplying both sides by the same thing, I multiplied both sides by dp, but then I divided by t. And as long as I use legitimate legal algebra, I can use whatever techniques I need to get the things on the sides that I want them on. Let's take a look at one more on the next screen. We haven't really done any applications yet, so let's take a look at one of those. A tank contains 20 kilograms of salt dissolved in 5,000 liters of water. Another word for salt water is brine. So this next sentence just means that more salt water is being added to this salt water. Salt water, or brine, that contains 0.03 kilograms of salt per liter of water enters the tank at a rate of 25 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. When they say the solution, they just mean this salt water mixture, right? The solution is just some solid dissolved in water. This is a salt solution. So the solution is kept thoroughly mixed and drains from the tank at the same rate. How much salt remains in the tank after half an hour? Not how much salt solution, how much salt. Notice that this tank originally contained 20 kilograms of salt. It happened to be dissolved in water, but there were 20 kilograms of salt. So we are looking for how much salt, how many kilograms of salt are in the tank after half an hour. The other thing that I've noticed right away here is that everything is given in kilograms, liters, and minutes. But all of a sudden they've given us half an hour. So I'm going to change that to 30 minutes. Since the thing that we want here is an amount of salt, let's let y of t equal the amount of salt in the solution at time t. By at time t, I mean after t minutes. We're actually told a couple of things. We know what y of t is when t is 0, right? When we first begin this experiment, or whatever it is we're doing here, we're told that a tank contains 20 kilograms of salt. That's the beginning of our process. Brine that contains salt is added or enters the tank, but at the moment that we begin, the tank contains 20 kilograms of salt. So y of 0 equals 20. What we're looking for is y of 30. That's what we're trying to figure out. How much salt is in the tank after 30 minutes? We know how much salt is in the tank after 0 minutes, and we're looking for the amount of salt in the tank after 30 minutes. Let's take a look at what our variables are here. I've said y of 0 and y of 30. 0 and 30 are both time, right? Y is clearly one variable, and the other one, and I've written it here as well, y of t implies that t is the input variable. After a certain amount of time, there will be y kilograms of salt in the tank. So I can talk about the rate of change of salt in the tank over time as a ratio of two differentials. The change in y, the amount of salt, over the change in time. So dy dt is the rate of change of salt in the tank, and we can write that as sort of a rate of salt coming in to the tank minus the rate of salt going out of the tank. Well, we know the rate in, it's 0.03 kilograms of salt for every liter that goes in. And we know that there are 25 liters of water or fluid solution going in every minute. This is our rate in. I can simplify this, and I get 0.03 times 25, which is 0.75 kilograms of salt per minute. But I still need my rate out. They tell us the rate that the new solution is entering the tank. It's 25 liters per minute. And they also tell us that the fluid or the solution drains from the tank at the same rate. So we have 25 liters of new solution coming into the tank every minute and 25 liters going out. So there's no change in the actual amount of fluid in the tank. That stays constant, but the amount of salt is changing. If the total amount of salt is y of t, the total amount of salt at any time t is y of t, then the amount of salt per liter is y of t over 5,000. So we have, I'll erase this. And then we have that the rate out is the total amount of salt in the tank over 5,000. That's in kilograms, that's in liters. But we still have a rate of 25 liters per minute. Then I can simplify this expression and I get, I need to erase my question mark. I'm in trouble with my pen tool again. White pen, okay. I have y of t over 200, and that is kilograms per minute. This then simplifies to 0.75 minus y of t over 200, all in kilograms per minute, and I now have a differential equation. I think I'll simplify this just one little step further, 0.75. I'm just going to write this as y over 200. And part of the reason for that is I want to remind you that this right-hand side here looks an awful lot more like what we've been solving, but y really is just a function of t, right? Remember that whole conversation we had earlier about y being a function, dy dt is a ratio of differentials, but y is a function of the other variable, right? So what we're going to try to do next is to solve for y. So let's rewrite the differential equation over here. And then let's try solving this without separating the variables first. Let's see what happens if we multiply both sides by dt, which lets me cancel those. And that gives me dy equals 0.75 minus y over 200 dt. It seems like that would be easy to integrate, and it would, but this would not, because here I have to integrate with respect to t, but my variable is a y. If you've had calculus 3, you could do this, but that's not the point. The point is that there's an easier way and a more efficient way now that we understand about separable differential equations. So let's do it this way instead. I think I need to give myself a bit more room. It's actually the story of my life. dy dt equals 0.75 minus y over 200. How could I get all my y's on this side and all my t's on this side? Well, there's no t here at all. So it's tempting to say, well, let's just add y over 200 to both sides. But that would give me y over 200 plus dy dt. And that is not going to do me any good at all. I can't integrate that. If I multiply both sides by dt now, I'm stuck. If I multiply both sides by dt before I do anything, I'm stuck. So we need to think of another way to do that, and that is to use some really basic algebra to turn this into a single fraction where I have t's on the top, if there are any, and y's on the bottom. Or if I have y's on the top, I can divide by y. If I have t's on the bottom, I can multiply by t, right? So let's do that. Let's turn this into a single fraction. I've done that here because when you multiply this quantity here by 200 over 200, you get 150. So 150 minus y all over 200, and now I can separate the variables. I'm not going to do that here because I'm out of room, but what I will do is provide the final general solution so that you can see what it is, and you can check your process going from here to that end step, and then we'll check the final particular solution again together. Okay, here's my final general solution. Y equals 150 minus some constant, I've called it k, times e to the t over 200. The thing is, we know what y is when t is 0. right? We figured that out down here. At t equals 0, y is the amount of brine, the amount of salt in the solution. So at time 0, it's 20. So I can plug in 20 for y and 0 for t. Well, that's just going to be e to the 0, and e to the 0 is 1. So now I have 20 equals 150 minus k. If I subtract 150 from both sides, I get negative 130 equals negative k. So k equals 130. And my final solution then is, what is y? 150 minus k, but now I know what k is, it's 130. E to the t over 200 when t is 30 minutes. I'll leave you to work out the details of this one because now it's just a calculator problem. And you could do this with a scientific calculator. You don't need anything specific. You don't need a graphing calculator. You don't need something that will do differential equations. I don't even know if such a thing exists. But I will tell you, so that you can check your own answer as you go forward, if you're interested, that this is approximately 31.8 kilograms. Well, that was a nice look at an application, how to take something like this and set it up so that you have a differential equation to work with. Most of the time, you'll just be solving differential equations at this point. But you will need to be able to resolve applications into differential equations as we go forward as well. So that was a really nice kind of introduction to that process. We do have one more thing to talk about in this section, and that is graphing integral curves. Those of you who joined us early and watched the videos in Chapter 1, or the videos from Chapter 1, will recognize these as being produced by something called direction fields or slope fields. In that video, we solved a differential equation, dy dx equals 2x, and we did that by multiplying both sides by dx. So we had dy equals 2x dx, which is very simple to integrate. It gave us y equals x squared plus c. And then I used that to graph a family of curves for which this function has solutions, right? It has solutions for every value of c where c is a real number. But it turns out that you can actually graph the differential equation after a fashion. You can graph it right from the very beginning. You take a look at what dy dx is for varying different values of x. In other words, you plug varying different values of x in and see what y is. Why do we do this? Well, that tells us what the slope is at various places. Now that we have a little bit more understanding what a differential equation is, though, we can do this with much more complex differential equations. And I'm going to go back and pull on a differential equation that we worked with at the beginning of this video. And that was dt dp equals p squared t. I'm not going to rework this problem because we've already done it, but I will write down the general solution that we came up with. I used k for my constant instead of c, and I wrote the solution as 1/3 p cubed. I'm going to change that slightly now just because it's a little tidier and write it as p cubed over 3. My exponent is p cubed over 3. The point of this video is to show how drawing slope fields or directional fields can help you determine the shape of your solution for the family of curves that it produces. So let's start by kind of refreshing our memory about what it means to draw a directional field. Here's the field I'm going to be playing on. I need to label it for my own benefit, my own satisfaction, and my own clarity here. My independent variable is p, so this is going to be my p-axis, and my dependent variable is t, so this will be my t-axis. Now, what this equation tells me is what the slope is at various places on the graph. Now, in the 1.1 example, I only had x to plug in, right? So I had to pick various different values for x, plug them into my equation that produced an answer, which was my slope for that value of x. In this case, though, I have both an input and an output variable. I have an independent variable and a dependent variable in my expression, in my differential equation. So I need to pick points on the graph where there's one of each. I can pick places where either the p or the t value is 0, but they don't have to be. So, for example, I'm going to pick a place where, well, let's just do a couple along some axes here. I've already labeled 3, 0. Remember that this is my input, this is my output. And I'm going to pick 0, 2, and then I'm going to pick 1, 1, because those are just randomly points that I chose, but having labeled them, having plotted them here, I'm going to use them. All right, so what does it mean to be at the point 3, 0 for this differential equation? It means that your slope at that point will be whatever the product of p squared, or 3 squared, is, and t, or 0, is. In this case, that's going to be 3 squared times 0, which is 0. So my slope here will be 0. That's a little tiny line segment. The smaller you can draw them, the better, but make sure you draw them so that they're long enough to see what's going on. You don't want them to be super long, but you don't want them to be so short you can't really tell what's going on. So it's a little bit long, maybe. Let's try that. All right, let's do the same thing now for 0, 2. If I plug 0 in for p and 2 in for t, I also get 0. That's going to be 0 squared times 2, which is 0. So at this point, I put that in the wrong place. This slope should be, maybe I'll use a different color, should be here. It's a little exaggerated because it's hard to distinguish it from the axis otherwise. At 0, 2, my slope is also 0. At 1, 1, however, I have 1 squared times 1, which is 1. And that slope is here. That's a slope of 1 at that point. Now, it's hard to get a feel for this from just 3 points. The goal would be to plot several, points in this entire field. So I'm going to go ahead and do several more, just so you get a feel for what's actually happening here. But then, while I may ask you to do this on a quiz by hand, I will do it for either a very simple differential equation or for a very small area, just so I know you know how to do it. Beyond that, we'll be doing these using a graphing tool, an online graphing tool. So let me just do a few more of these. I'll go grab my white pen again, and let's pick some more points. How about, let's just stay in quadrant 1 so we can focus on the technique here rather than anything else. I'm going to plot, or I'm going to find slopes for these points. I may not do them all on screen. I think that's a little tedious. I'll go and do them off screen. I'll do a few on screen, and then I'll do the rest off screen so you can see what's happening. Let's do this one next. That's the point 2, 0. That's 2 squared times 0, and that's 0. And I don't know if you can tell, but I've already noticed a pattern here, and that is that anytime there's a point on the x or the p axis, because that p is a factor in my right-hand side expression, that slope is always, this is always going to be 0. Same if t is 0, right? This result will always be 0 if t is 0. So that means I can plot all of these as well. So I have some slopes there for those values of p or t. So I don't need to do any more with any zeros in them. Let's do 2, 1 and 2, 2 and 1, 2 together. Then I'll go back and do a few more off screen. 2, 1 is 2 squared times 1. 2 squared is 2 squared times 2. 1, 2 is 1 squared times 2. That's 4, that's 8, and that's 2. So my slope at the point 2, 1 is 4, pretty steep. At the point 2, 2, it's very steep. At the point 1, 2, it's a lot shallower. Not that shallow though. Steeper than 1, but shallower than 4. So it looks something like that. So I don't know if you can see that what's happening here is that the curves that will follow this are sort of sweeping up here. They're steep here, less steep here, but if you start anywhere and follow from one sort of slope indicator to the next, you can see you're going to be sweeping up. So let me just do a few more of these off screen. All right, I've done some more where the P, the input variable is 2. So at the point 2, 3, my slope is 12, very steep, and steeper still at 2, 4. At 1, we had already done 1, 2, and so I kind of copied that over and moved it so I can start a new list. Right? I did 1, 2, and found the slope was 2. I'd already done that over here. And then I did 1, 3, and I found the slope was 3. And I noticed, oh gosh, my input's always going to be 1 squared times whatever this number is. So at 1n, my slope will always be n. That means that at 1, 3, my slope will be 3. At 1, 4, it will be 4, and so on. Now I'm going to go do a few more where the input is 3 and 4. Well, I haven't finished that either because my slopes are getting very, very steep. At 3, 1, I have a slope of 9. At 3, 2, I have a slope of 18, 27, 36. They're very, very steep. And at 4, 1, I have 16. And my work here is not accurate. I'm not actually trying to figure out, for every 1x, I have 16. I can't really do that with any kind of accuracy. But what I have been able to do is show the general trend that my curves will take based on what their slopes have to be at any given point. If I graphed this instead, what I would get would be something like this. When k equals 1, I get t times e to the p cubed over 3. Well, e to the p cubed over 3 looks something like this. At 0, that's when p is 0, t is 1, just as with any exponential function, right? The e to the power of 0 is 1. And when k is 1, I get 1 times 1, which is 1. So that's there. When I plug in 1 for p, I get something like 1.4. E to this power is 1.4. And then when I plug in 2, it's like 15 almost. So it goes way off the charts. That's when k is 1. Since there's actually only one member of this family, this curve is actually really very interesting. It doesn't just come down like this. It does this. So where does it go to? It goes to about 2 when it does that. It's got a little bump in it. All right, let's do another graph for the value of k being 2. Here, when p equals 0, I get e to the 0 power times 2. So I get 2 for my y-intercept. And when p is 1, I get about 2.7. When p equals 2, I get 28. So again, it's way off the charts. It's even more steep here, even more steep for k equals 2 than it was for k equals 1. Let's try this now for a value of k equals a fraction, because the larger k gets, clearly the steeper my graphs are going to get. Let's do k equals maybe 1/5. For this graph, when p is 0, I get 1/5. I can't remember what that was. Then I get, well, I can't remember what that was either, 2.9, I think. And then the next value is 1620. 1,620. But to get there, I had to go all the way out to p equals 3. So this function looks like something like this for various different values of k. When k equaled 1, I got the pink graph. When k equaled 1, I got the yellow graph. When k equaled 2, I got the pink graph. And when k equaled 1/5, I got the green graph. My observations about the slopes of these graphs were not accurate. When I was graphing the slope field for the differential equation, I didn't do a very good job necessarily graphing my slopes, but you can see that these slopes get steeper and steeper and steeper. For p equals 1, for my input value equals 1, different k values give me steeper and steeper slopes. So at this point, one function has a shallow slope, another one higher up has a steeper slope, and another one has a steeper slope still. And the same is true out here, but starting out steeper, or starting out, I can't remember now which slope that was. But the slopes do eventually get steeper as you go out here as well. But you have to go out, in this case, to p equals 4 to get a slope this steep, whereas that slope is way out here. For p equals 1, it has it's for a different value of k. I don't know, that may be a little confusing. The point really, though, that I want to make here is that these slope fields, the differential equation and the slope field, which is something about the slope at various different points, p comma t, tells us something about the behavior of the graph itself. And it may not always be that we want to see a family of curves, but general behavior at a point. And so slope fields can be very useful for a lot of different things. These curves that we graphed here, the family of curves that come from the original equations, these are sometimes called integral curves. So if you were asked, for example, to find an equation for the integral curves of a differential equation, the integral curves of this differential equation, this is that solution. This is that equation. This equation is the equation for the integral curves of this differential equation. It's another way of saying solve the differential equation for the general solution. The integral curves are the curves that result from graphing some sample curves from this family of curves. It's a family of curves because we don't know what k is. Other times you might be asked to draw integral curves. Well, that's what we've just done here. This pink, yellow, and green graph are several integral curves for this differential equation. Other times you might be asked to find a particular solution, or the solution passing through a specific point. Let's say for this one, we wanted to find the solution passing through the point 0, 1. Well, having graphed it already, I can say, well, here's the point 0, 1. So the solution satisfying that requirement is this solution here. Right? It's this solution, it's this graph, rather than one of the other graphs. If I haven't graphed it already, then I can do that just by plugging that point in here. The point 0, 1 tells me that t equals 1 when p equals 0. So I get 1 equals k. And that tells me that t equals e to the, p cubed over 3 is the solution, the particular solution that occurs at this point, the point 0, 1. So this graph, this large white graph, is the particular solution that represents this algebraic version of the particular solution. So I might ask you to represent that particular solution as a graph or as an equation. Well, this was a much longer video than I intended, but we've covered quite a lot of ground. We've talked about what separable equations are, separable differential equations. I've shown you several examples. We've worked through those examples. I've given you a couple of anomalous examples, ones that don't look at first like they're going to be separable, but turn out to be separable. We've done an application, And we've talked about integral curves and particular solutions in the context not just of the algebra, but also of the graph. So we really covered a lot of ground in this. And I feel like this is a really good introductory video, not just for separable differential equations, although that's been our focus, but for differential equations in general. So that's enough for now, and we'll talk about the next big picture in the next video.